Why are large datasets from CFD simulations so hard to manage? Imagine running a simulation that models airflow over an airplane wing or water flowing through a turbine. The results can be mind-bogglingly detailed, but managing that data is a whole different story. When engineers use computational fluid dynamics software to analyze fluid flow, they often generate massive amounts of data. These datasets can reach tens of terabytes for complex models with millions or even billions of mesh cells. That's like trying to store and organize a library of thousands of movies. The first challenge is storage. High-fidelity simulations, especially those involving turbulence modeling or large physical domains, produce enormous files. These files need special storage solutions that are fast and reliable. Without proper infrastructure, accessing or sharing this data becomes a real headache. Then there's the computational cost. Running these simulations takes a lot of computer power. It can take hours, days, or even weeks depending on the size and complexity. During this time, the computer is busy crunching numbers, and the data output keeps growing. Managing that output requires careful planning to avoid bottlenecks. Data structure adds another layer of difficulty. CFD data isn't just simple numbers, it's multidimensional. It includes spatial coordinates, time steps, and multiple physical variables like velocity, pressure, and temperature. Without organized metadata and clear formats, it's easy to get lost trying to interpret or reuse the data later. Post-processing is another big hurdle. Once the simulation finishes, engineers need to analyze the results to find flow patterns or pressure points. Handling large datasets during visualization can slow down hardware and software. Extracting specific information without losing accuracy demands careful data management. Increasing the detail of a simulation also makes managing data harder. Finer meshes and more complex physical models mean more data. For example, using turbulence models like hybrid Reynolds averaged Navier-Stokes and large eddy simulation can give better results but at a huge cost in data size and computational resources. Engineers have to find a balance between getting detailed, accurate results and keeping data manageable. Uncertainty and error analysis add even more data layers. Quantifying how accurate the results are involves storing additional information about numerical methods, boundary conditions, and mesh quality. This makes datasets even larger and more complex. Emerging techniques like machine learning and advanced hardware are being explored to handle these large datasets more efficiently. But these approaches requiring new workflows and often face hardware limits. For mechanical engineers, managing large CFD datasets is essential for designing better turbines, vehicles, or pumps. Proper data management speeds up design cycles and helps make smarter decisions. It takes investment in good storage, processing tools, and smart strategies to keep everything organized and accessible. So, the main reasons these datasets are tough to handle are their size, the heavy computational demands, complex structures, and the need for detailed analysis. All of these factors make managing CFD data a challenge but also a vital part of modern engineering work.